Hi class, welcome back to Intro Stats. Today we're talking about variability and quantifying the spread of scores or the dispersion of scores. So when we talk about variability, what we're really talking about is the way that the scores spread out whenever you look at them visually or even when you just think about them conceptually. And there are three measures of variability that we're going to cover: the range, the variance, and the standard deviation. We're going to start with the range because it's possible that you've been introduced to this, and so it allows us to connect with your existing knowledge and then kind of build on that. In case it's been a while since you were introduced to it or you never were introduced to it, the range is the difference between the highest and lowest scores in a sample of data or a population of data. And here you see that when we're talking about difference in statistics, sometimes we'll use abbreviations, and you see the Greek letter delta. It looks like a triangle. And that indicates that we're doing the difference between two things. So in this set of data, we have a normal distribution. We have 64 scores. You can see I've labeled each one. So we have x1, x2, x3. We're going to assume that these represent scores on an exam. So the lowest score was 72. The highest score was 100. And for the range, we're just looking at the difference between the highest and the lowest score. So if we take 100, we subtract 72, we find that the range is 28. In statistics, for most of what we do later on when we're doing tests, we don't actually use the range, although we sometimes use it to describe our sample. But when we actually want to do calculations and we want to do a statistical test, what we rely on builds from deviations. And deviation is basically just a fancy word talking about the difference. And in this case, we're talking about deviations between each individual score and the mean. So in this group of data, I can tell you that the mean is 86 because it's a normal distribution. And we'll talk about that more whenever we get into hypothesis testing. But a normal distribution centers around the mean. So the middle score here, it's symmetrical. So it's easy to identify the middle score. There's a few scores above it, a few scores below it. The scores are increasingly less likely as you get further and further away from the mean. So a score of 100 happens less frequently than, say, a score of 88. And it's such that there's symmetry where the likelihood of a score that's 24 points above or 24 points below the mean should be relatively equal in their frequency, their likelihood of occurrence. So what we would do is we would pick any individual score, and if we were doing this in a population, we subtract the mean, and we note that the mean is mu, and I introduced that in an earlier video. So we have x, and again, that's any x, so x1, x2, x3, and sometimes you'll see this as xi minus mu, because we can do the deviation for any score. Within a sample, it's basically the same formula, x for any score minus the mean, except the mean is represented by x bar instead of mu. So let's take the first score, x1. x1 is a score of 72. If we subtract the mean of 86, we find that the deviation for this is going to be negative 14. By contrast, if we look at a score on the opposite end of the distribution and we say what's 100 minus 86, we see that we're going to end up with positive 14. The scores that are below the mean will automatically have a negative deviation. The scores that are above the mean are going to have a positive deviation. And we'll talk about the implications of those negatives and positives and how they cancel each other out in a moment. So let's look at how we do this. Basically, I've taken the scores that were represented in that distribution. So we have them going from 72 to 100. You'll note there's 172, 274s, 376s. I'm just representing that same data, but in a table. So I have 172, 274s, 376s. And if you compared, you should see that this matches the data that's in that table that you just, or the chart that you just saw. So because we're working with a sample, we're going to indicate that x minus x bar is the formula for deviations. We've already indicated that x bar is 86. So if I take 72 minus 86, I get negative 14, and we saw that earlier. And then 74 minus 86, negative 12. 76 minus 86, negative 10. And then if I look at the other end of the distribution, 100 minus 86 is 14. 98 minus 86 is 12. 96 minus 86 is 10. So we can see that they're, again, it's symmetrical. Negative scores are going to be happening if it's below the mean. Positive scores are going to be happening if it's above the mean. And so these scores basically are canceling each other out, which means that if I want to understand about the overall variability in my data, I'm going to have to do another step, because if I just added these together, if I just summed these deviations together, I would get 0. And I would get 0 for every distribution basically. And so I would never know anything really about the variability, at least not the cumulative variability within the data. So to deal with this, we take our deviation and we square it. And by squaring it, all the negative numbers are going to become positive, because if I multiply negative times a negative, I end up with a positive. And if I multiply a positive times a positive, I also end up with a positive. So now, negative 14 squared is 196, but also positive 14 is 196. So basically what we've done is we're ignoring the direction of the deviation. We're just paying attention to the magnitude of the deviation so that we can add them all together, sum them all together. We see that scores that are considerably above or below the mean have larger deviations and also larger squared deviations. So as I get further and further and further from the mean, I deviate more from it. The score, this deviation or squared deviation, is going to be larger in magnitude. So 100 deviates more from 86 than 90 does. And in fact, for all of the scores, for all of the x's that are right at the mean, x bar of 86, the deviation is going to be 0. Once I have these deviations, the next thing to do is to add them together so I have an estimate of the overall variability that's in my data. So you can see here that we're building on these formulas where initially I do the deviation or the difference, I then square that difference, and then you see sigma, and we've talked about this before when we were doing the mean, where sigma x, we add together all the x's. Here, sigma of the square deviation, we're going to add together all these square deviations, sum those up, and that's going to give us the sum of the square deviations. We often abbreviate that as sum of squares, or SS, but if you're reading a stats textbook, you may see it written all the way out, sum of square deviations. Those three things all mean the same thing. In this case, when we add together 196 plus 144 plus 144 plus 100, we do that for all of our deviations, our square deviations, we find that the sum of squares is equal to 2,688. This number will naturally grow larger as we have more scores in our sample or more scores in our population. So we need to adjust it. We need to account for the number of scores. And the next step does that. So we have the sum of squares, and we use those to get the variance, which is the average square deviations. So when we did the mean, when we got an average, we took the sum of x, we divided by n. We divided by the number of scores. We're going to do that same thing here, where we're going to take the sum of the deviations, the square deviations, and we're just going to divide by the number of scores that we had to account for that. Because again, all things being equal, the more scores that I have here, the larger this sum of squares estimate will be. And so I need to put it in a frame of reference, put it relative to the total number of scores, kind of like when we were doing relative frequencies, for instance. So we're basically just putting it in relation to the total number of scores so that we can better understand it. So for a population, this is relatively easy. We have the lowercase sigma squared. That's the abbreviation that we use to represent the variance. And we have the sum of squares as our numerator, and we have n, the number of scores, as our denominator. We just divide the sum of squares by n, and we get the variance. For the sample, we do need to pay attention, and I've mentioned this once before, but in a sample, the variability tends to underestimate the total variability in a population. If we're talking about IQ scores, the likelihood that we get somebody that's extremely, extremely high or extremely, extremely low is less than what actually exists in the population, because certain types of individuals aren't going to be in our study, they're not going to volunteer, They maybe can't volunteer. If you have a really, really low IQ, it's possible that they couldn't even consent to participate in the study. And so, because of that, it's possible that, and in fact, through dozens of studies, we have seen that samples underrepresent the variability in the population. We have to deal with that. To deal with that fact that we underrepresent the variability in the overall population, and we want this variance estimate to approximate the population, we need to subtract 1. And the nice thing about subtracting 1 is as n gets larger and larger and larger, the impact of subtracting 1 gets smaller and smaller and smaller. So if I subtract 1 from 10, I'm subtracting 10%. That's a pretty big deal. But if I subtract 1 from 100, I'm only subtracting 1%. So the impact to the final quotient, right, the impact to the answer here, the impact to the variance estimate is going to be smaller when n is larger. Well, as I get more people in my sample and my sample gets larger, assuming that I'm properly sampling and that I'm sampling randomly and there's not bias or something, it should be the case that as n gets larger and I sample more and more people from my population, that sample is going to do a better and better job of approximating the population. So my estimate of the variability from the sample variance should get closer and closer and closer to approximating the variability in the population. And by subtracting 1, again, it acknowledges the fact that as this n gets bigger and bigger and bigger, we need a smaller adjustment. And as n gets larger and larger and larger, if we keep subtracting just 1, proportionally, that 1 that we subtract is going to be smaller in relation to the total sample size. So pulling from what we've already done, the numerator here is the sum of squares, right? Sigma x minus x bar squared. And we already know that that's 2,688. We then know that there's 64 scores. If you looked in the very first slide when I introduced the distribution, they were labeled x1 through x64 numerically. So we had already counted those. And so we take 64, we subtract 1, and we just divide 2,688 by 63, 64 minus 1, and that gives us the variance estimate. Now, the last step, this is going to give us the average squared deviation. But if we want to know about the average deviation in our sample or in the population, we need to shift it back to our original units. Now, the nice thing is this is relatively easy. If I have squared deviations and I want to shift it back to the original units, all I have to do is take the square root. So here we see sigma squared. Again, for a population, that's the variance. We just take the square root of the variance, and that gives us the standard deviation. Now, I should note what that also means is if somebody gives you the standard deviation, and for some reason you need the variance, all you have to do is square it. And so you can easily go back and forth just by squaring and square rooting. Again, as I've said a couple of times, the math in this class is not the most difficult part. It's really the conceptual part of hypothesis testing that we'll get into later. So develop this, practice this, get comfortable and familiar with this. If it's been a while since you've used these math skills, you may need to go back, practice those, practice PEMDAS, remind yourself about all those things. But once you do that, it's really the things between exam 1 and exam 2 is the part where you need to kind of focus in, start paying attention closely to this new material that's coming in. So similar to the way we have this for the population, if we're working with a sample, it's the same idea. We take the variance estimate, which is noted as s squared for a sample, we take the square root of it, and we get s. If you're reading a stats textbook, that's probably what you'll see. However, if you're reading in a journal article, standard deviation is often noted as a capital SD. And of course, anytime we're using a normal Roman letter, we're going to use italics. So if you're using a Greek letter, you're going to just leave it by itself. You don't need to italicize for proper APA. But because S and SD are both just normal Roman letters like we use, you need to italicize.